You can see what everybody else is sort of thinking about. So, you know, here we are. Nice to meet each other. Yuck, yuck, yuck. Okay, so here's one that will test your understanding a little bit, maybe. Joules are to gallons as watts are to what? Shall we choose speed in feet per second, or water pressure, which would be like, you know, pressure of the water somehow, or flow, gallons per second, or a volume, cubic feet. Volume would actually be sort of, you know, analogous to gallons. It'd be like inches and miles are both the same units or something like that. So it looks like we have convergence of opinion here. So, you know, if you started out with the wrong answer and suddenly you realize that everybody else thinks differently from you, that's going to shock your forebrain and induce you to learn something. That's the theory here. The right answer is indeed flow. So a joule is a unit of energy. It's some number. It's some amount of energy, and watts is a unit of energy flow. So joules per second is what watts are. So we have managed to get there. Good job. Albert Einstein. He said, "God does not play dice with the universe." Was he right or was he wrong?
Was he right?
Sorry? Was he right or was he wrong? Is that true or is it false? Does God play dice with the universe? Let's leave aside the whole existence of God thing, all right? We'll just start from like dice. Dice with the universe. Was he right or not about that? Well, according to quantum mechanics, God or whomever does indeed play dice with the universe. There's the things that we think of as solid particles have this wave character, and the wave is actually sort of a probability wave. So the wave function of an electron going through the two slits of the slit experiment said that there was a 50% chance it was going to go through one and a 50% chance it would go through the other. So the value, you know, it's like the value of this wave function, its number at each of the slits is 0.5. And so it's essentially a random process, and it's actually going through both of them unless you observe one or the other, in which case it collapses the wave function, so the probability becomes 1 wherever you see it and 0 wherever it was not. And so, but in the unobserved state, it's a lot like a game of dice. So Einstein apparently was wrong about that. The answer here is false. Okay, this is the expression for our very first climate model that we developed in class last time. So we've got, you may recall, and we're going to start from here again, there's the solar constant, 1 minus albedo. That's how much is reflected. This factor of 4 right here is because of the geometry of the problem. The sun is coming in a single direction, and the energy from infrared is going out in all directions. And the area of a circle, which is the shadow that the sunlight hits relative to the area of the surface of a sphere, is just this simple exact factor of 4, which is an amazing thing. It's like the sun shining on the earth is only shining on average at full intensity 1/4 of the surface of the sphere. Of course, it's shining on half of the sphere, you know, the light half, but it's not as strong, you know, around the edges of the sphere because the ground is sort of tilted relative to the way the sun is coming in. So that sounds like a complicated problem, and it just astonishes me every year when I get to this part in the class that the difference between the area of the circle and the area of the sphere is just this simple exact factor of 4. Anyway, that's where that comes from. So this is energy in on the left-hand side and energy leaving by infrared going in all directions on the right-hand side. And so from this model we extracted a temperature of the Earth, and it was too cold, as you may recall. But there's still a lot of stuff things that can change the climate of the Earth that you can sort of represent in some crude way in this very simple climate model. So the options are urban haze, that's A. B is clouds. C is the sunspot cycle. D is greenhouse gases. And then E is urban land use changes. So I've been a little slippery with you here. Actually, there are multiple correct answers. There's actually only one answer that is incorrect, and that is greenhouse gases. But urban haze can affect the temperature of the Earth by scattering sunlight back out to space. We've got perversity here. This is great. It's a rainy day. Let's all choose the wrong answer and kind of, yeah, I know how that feels. I'm with you. Oh, B. You got B. B is clouds. Yes. Okay. I'm sorry. I was thinking. I'm sorry. I'm an idiot. So urban haze is a way of cooling down the planet that we'll learn about. Little particles in the atmosphere tend to reflect sunlight back out to space, and so that changes the albedo of the Earth. And so albedo is this term right here. It turns out that aerosols, little droplets of actually sulfuric acid that come out of coal-fired power plants are an important thing that is affecting the climate of the Earth. It tends to cool the climate of the Earth by reflecting sunlight. So A is a good answer. B is a good answer. Clouds and ice are the two main things that determine the reflectivity of the Earth, the albedo. So, you know, clouds is certainly probably the best answer here because it's the biggest thing that can affect the climate. C, the sunspot cycle, also turns out to be correct in that, as we'll talk about in the future, the intensity of the sun varies a little bit through this 11-year sunspot cycle. Not a whole lot, but a little bit. And so you can vary the intensity of the sun and affect the climate of this simple model just by changing the L term here, right there. Greenhouse gases have no place in this model yet. That's our job for today, is to rectify that. And then urban land use also can affect the albedo of the planet. There's something called an urban heat island effect, which is partly due to the albedo of the surface. You cut down a forest and put up a parking lot. You know, you change how the sunlight is absorbed or emitted, and that change in the albedo could be folded into the albedo term there. So with that, we'll sort of continue on. Just to start, on the same page here, so this is the equation for that simple climate model, which balances the energy and calculates the temperature. And this is what we're going to modify today to add a greenhouse effect. Now, the units of this are in watts on both sides. So this number here, L, the solar constant, is watts per square meter. And this is units of meters squared. So those meters squareds cancel, and sigma T is watts per square meter per Kelvin raised to the fourth. And this is Kelvin raised to the fourth, so those go away. And then here's our square meter again. So we got watts and watts, so that's good. what I want to do now is to put this back in terms of watts per square meter average for the Earth's surface. So I want to divide by the area of the sphere. So that will now give us this expression in units of watts per meter squared again. And what it will do is make it simpler to draw cartoons, because I don't have to draw spheres anymore and shadows and all that sort of stuff. So dividing both sides by the area of the sphere, we end up with that. And you see that the pi r squareds, so there's a 4 on this side, and there's no 4 on this side, and so we've ended up with this kind of mysterious little factor of 4 on the bottom there. Yes? Why do I want the units to be watts over meter squared? Because I want to draw pictures that do just 1 meter squared of the Earth's surface, and I want to put an atmosphere here and draw some arrows that are carrying light around. And to do that over a sphere is just too much for my artistic abilities. Yes?
Is that grams? Is that second part of
No, ground, sorry. Another thing that I'm going to do is put in an atmosphere. And there's going to be a temperature of the ground and a temperature of the atmosphere. And so I've put in that subscript there in order to leave room for myself to have 2 different temperatures. So we have now, all we've done is taken our model and expressed it in terms of 1 average square meter of the Earth's surface. And it all still works, but we're just simplifying it so that I can draw cartoons better. Okay? So, and that results in this mysterious factor of 4, which is the difference between the circle and the sphere area and all of that. Okay, so the greenhouse effect. We're going to have the ground, and the sunlight is coming into the ground, and so the energy flux coming into the ground is, as it was before, it's L times 1 minus alpha over 4. And the ground is going to shine in infrared light, just like it did before. And the rate of energy flow there, the watts per square meter, is epsilon sigma temperature of the ground to the 4th, just like before. Now what we're doing now that's different is we're going to put a pane of glass to represent an atmosphere. And it's going to sort of hang there magically above the ground. It's going to be not in contact with the ground, so it can have a different temperature than the ground. And it's selective about how it deals with light. It lets the visible light go through, but it traps all of the infrared light. So this infrared that's coming from the ground is going to get absorbed by that pane of glass. And the pane of glass is going to itself emit infrared light according to its own temperature. So Let's make some room. This. So the pane of glass is going to shine infrared light, and that will be an epsilon from the atmosphere times sigma temperature of the atmosphere to the fourth. So these epsilons are just 1. We're just considering them to be 1. Maybe I will make our lives a little less cluttered and just assume that they equal 1, and so we can kind of drop them. Save on board space. So the pane of glass is emitting light going upward according to the temperature of the atmosphere. But now here's the tricky part, and here's where the whole thing comes from, the whole greenhouse effect. The pane of glass is also shining light downward, also at a rate of sigma temperature of the atmosphere to the fourth power. So what we have now is a problem that has 2 unknowns in it. See, before we just had one unknown, which was the temperature of the planet, the temperature of the ground. But now we have 2 separate temperatures that we can calculate from this model. And the way you calculate, in a system like this, where you have multiple unknowns, is to come up with multiple equations. So in algebra, if you have 2 unknowns, you have to have 2 equations that are sort of independent of each other in order to specify them. It's kind of like if you have, you want to find a point on a plane, one equation is a line and another equation is another line, and where they intersect, that's a point. So if you just have one equation that's one line, it doesn't tell you which point it is because it could be anywhere on the line. But when you have multiple equations, you can solve for this. So the equations that we're going to pull out of this come from energy budgets of the various pieces of the system. So the way we worked it before is the energy coming into the Earth had to balance the energy going out of the Earth. And that's still true. We're going to have an energy budget for the Earth and an energy budget for that pane of glass. And so that's how we're going to get these equations. Yes?
Is the pane of glass emitting infrared light? Is that
Yes. Yeah, that's what these are. I'm drawing infrared as the wiggly lines because they're longer wavelength, and kind of they do that sometimes, draw infrared as wiggly lines. But yes, that's where that is. So sigma T of the atmosphere to the fourth, if it can absorb infrared coming up from the ground, it also can emit infrared. That's the sort of two-way street nature of the interaction of light with the electric field of the atoms in the pane of glass that we talked about. Okay, so let's write some of these budgets and try to see where they come from. And then we can go about trying to solve them. So a budget for the atmosphere. The atmosphere is that pane of glass there, and we have energy coming into the pane of glass. The only arrow that's going into that pane of glass is this one, coming up from the ground. So on the inside of this budget, we have sigma temperature of the ground raised to the fourth power. That's the energy flux represented in that arrow. So the energy going out from that atmosphere, there are 2 arrows going out. One of them is sigma T of the atmosphere to the fourth, and this is going up. And then the other one is sigma temperature of the atmosphere to the fourth, and that's going down. And of course, those are the same because they have the same temperature. And so we could just simplify that to sigma temperature atmosphere to the fourth. Everybody see where that comes from? Yes. Can you say your question again? I couldn't quite.
Is the atmosphere represented in the picture?
The atmosphere is this. So we're just counting up the arrows going into and going out of that pane of glass. Yeah?
Why does all the sunlight go into the atmosphere? Why doesn't any of it get absorbed into the atmosphere?
Well, in reality, some of it does. But in this simplest possible model of the greenhouse effect, we're saying it doesn't. But next week in lab, you're going to solve a case for nuclear winter where all the sunlight gets absorbed in the atmosphere, and you will see how that changes things. It makes it very cold at the ground. It's a good question. There was another, no doubt, good question around here someplace I thought I saw. Oh, okay, good. All right. So that's a budget for the atmosphere. We can also write a budget for the ground. So coming into the ground, we have the solar, which is L times 1 minus alpha over 4. And we also have another arrow coming into the ground, which is here, which is coming down from the atmosphere. So that is sigma temperature of the atmosphere to the fourth power. So that's adding up all the arrows going into the ground. And there's only one arrow leaving the ground, and that's sigma temperature of the ground to the fourth power. So it turns out that these are independent equations, like the two equations for the line on the graph that we were talking about. And given, a nice sharp pencil and a good attitude, you could do substitution and algebra and calculate what the temperatures of these two things should be. But there's an easier way, there's sort of a strategic way to approach this that makes it algebraically much simpler, and it also makes it kind of easier to understand what's going on. So I'm going to show you the easier way to do it. But you don't have to do it the easy way. In principle, these two equations are independent and could get you there. So the way to do it that makes it simplest is to draw a sort of imaginary boundary between the planet and outer space. And the energy going into the Earth system, no matter what happens to it inside there, has to balance the energy leaving the Earth system across that boundary to space. So let's leave a little room here. And draw that boundary to space. So looking a budget for Earth overall, sort of boundary to space. The boundary budget. The only one that's crossing the boundary going in is the sunlight. So that means our L times 1 minus alpha over 4, the intensity of sunlight averaged over the Earth's surface. That's all that's coming in across that boundary. And all that's going out across that boundary is what is leaving from that pane of glass, from the atmosphere. The sunlight or the infrared that comes from the ground in this simple model is entirely absorbed by the atmosphere, so it doesn't really do anything here. So the only one coming out is sigma temperature of the atmosphere to the fourth power. So So we got this equation by kind of looking at the cartoon and thinking about it. You could also get it algebraically. You could take these two equations, there's equation 1 and here's equation 2, and you could combine them using algebra and get to the same result. We haven't kind of put anything new into the problem here. But the cool thing about doing it this way is that this expression here has only one unknown in it, and that's the temperature of the atmosphere. So we don't have to do any algebra really anymore to solve for multiple variables at the same time, simultaneous equations. One equation and one unknown is a lot easier than two equations and two unknowns, right? So we're going to start from that equation and just solve for the temperature. And you should be having a nice deja vu now, because this expression looked a whole lot like the expression that we did on in the last lecture, where there was no greenhouse effect and no atmosphere. Here we had L times 1 minus alpha over 4 equals sigma temperature of the ground to the fourth. And this is exactly the same as this, except now we're talking about the temperature of the atmosphere instead of the temperature of the ground. So when we solved this last time to get the temperature of the ground, we found that it was too cold to represent the Earth overall. It was something like 253 Kelvin, which is like minus 15 degrees Fahrenheit. It's too cold for the average temperature of the Earth. But it was what you get by solving this equation for the temperature of the ground. And this equation for the temperature of the pane of glass is exactly the same, so we end up with the temperature of the atmosphere equals that same number, 253 Kelvin. So this is mathematically convenient, but it's also it's sort of illuminating conceptually as well, because one of the other problems you're going to be doing in lab next week has a ground and two panes of glass. So you've got arrows all over the place. So it makes the greenhouse effect a little stronger, you'll find out. And it gets more complicated because now you've got 3 different temperatures to calculate. What a nightmare. But the top temperature is always going to be that same 253 Kelvin. Because the top temperature, the temperature at which the Earth is radiating to space, it has a job to do of balancing the incoming sunlight. Whatever happens down deep in the bowels of the atmosphere is kind of irrelevant. Ultimately, what comes in from the sun has to be balanced by what leaves from the top of the atmosphere. So this top, whatever the top layer is, we call that the skin. So the skin temperature, the temperature at the skin, whatever that is the same. With no panes of glass, just the bare rock, the skin is the ground. One pane of glass for our simple greenhouse, the skin is the pane of glass, and the temperature is the same. And then in the problem you work in lab where there's 2 panes of glass, the top one is the skin, and the temperature is the same. Does that make sense? It's got to balance the sunlight. Yes? When it emits. Yes, it generates infrared light. If you heated it up as hot as the sun, it would generate visible light, but it's cooler than that, so it's generating infrared light. And the light can go through a vacuum, no problem. It's the only way to get energy through the vacuum. That's why we're not thinking about the other means of getting energy through, like conduction and all of that. Light is kind of, where the action is here. So yeah, it's emitting light into the vacuum, and we're sort of assuming that there's sort of vacuum between these panes of glass in this simple model, just to sort of keep things simple. And where we'll go in the coming couple of weeks is talking about real greenhouse gases and the real atmosphere and how that all changes things. But you can't really understand the greenhouse effect in all of its complexity without first understanding it in its simplest possible way, which, believe it or not, is what I have here on the board. Okay, so what a mess. Let's see if we can tidy up a little here. Clean slate. So here's our cartoon. And we have found the temperature of the atmosphere equals the temperature of the skin temperature, which is only set by the how bright the sun is and the albedo. Now we want the temperature of the ground, because that's the other unknown in this problem. So we're going to look at, this is the other part of this sort of trick, strategic way to approach this, is to work down from the top. So we're going to look at the budget for the atmosphere. So this is the boundary. So the budget for the atmosphere from right here is it's from equation number 1 here. Going into the atmosphere again is there's only one arrow going into the atmosphere, so that's sigma temperature of the ground to the 4th. And then coming out of the atmosphere, there are 2 arrows, and so and they are each equal to sigma T of the atmosphere to the 4th. And so that's a simple relationship between the temperature of the ground and the temperature of the atmosphere. And we already know the temperature of the atmosphere. So it turns out, so let's divide by sigma on both sides and then take the 4th root of both sides. So the 4th root, what we end up with is the temperature of the ground is equal to the 4th root of 2 times the temperature of the atmosphere. So this thing right here is it's like a square root sign, but you put a little 4 there. That means you're looking for the 4th root, the number that you multiply by itself 4 times, and it gives you what's underneath there, 2. It turns out that the 4th root of 2 is something like 1.18. You know, it's a number bigger than 1. So that tells us that the ground temperature is 18% higher on an absolute Kelvin scale than the temperature of the atmosphere. So temperature of the atmosphere is 253 Kelvin. The temperature of the ground is 253 Kelvin times 1.18. So it's warmer down on the ground than it is in the atmosphere. One thing you should be aware of, going through this in the textbook, the publisher dropped the little 4 there, so it looks like a square root, and it may mystify you, but there's supposed to be a little 4 there in the derivation in the text that shows you 4th root. So it should be kind of clear kind of where that comes from. Now you may wonder, what is it about that pane of glass that warms up the temperature of the ground? The pane of glass isn't creating energy. It's not a heat source. The way to think about a lot of things in natural sciences and a lot of things that will happen in this course, there's this analogy that sort of helps to think about why, something like a pane of glass. Good, huh? Got it on camera too. Why a pane of glass could warm up the ground. So there's this analogy that I use about 6 times in the course of the class. called the sink analogy, which is you have a sink like in the kitchen or something, and there's a faucet that's spraying some water down into the sink, and the water is running into the sink, and it's sort of piling up in the sink, and it's going down the drain. So you got water coming in, you got water going out. And the water going in is sort of an external driver to the thing. You know, the sink doesn't have any say in how hard you turn on the faucet. It's like the planet Earth doesn't have any say in how bright the sun is. It's sort of like this thing from the outside that's driving everything. But the rate at which the flow down the drain depends on the water level in the sink. The deeper the water gets, the more pressure there is from the weight of the water pushing it down the drain, and the faster it will flow out of the sink. So let's say you start and the sink is empty, and you turn on the faucet, and in that first instant there's more water flowing into the sink than is flowing out, and so the water level in the sink sort of builds up. So it builds up until it's deep enough that it can push water down the sink just as quickly as it's coming in from the faucet. So this is just like energy flowing into the earth, and then the rate at which the energy leaves the earth depends on the temperature of the earth, which is just a measure of how much energy there is, how much heat energy there is in the earth. So it's analogous to the water here, where the rate at which you get rid of it depends on how much has sort of accumulated in this sort of transient pool. There's water flowing through this all the time, energy flowing through the earth all the time. Now the greenhouse effect doesn't mess with the way that the energy comes into the earth. You know, the sun is still as bright as it was, but what the greenhouse effect does is it messes with the way that the energy leaves the earth, and it's analogous to putting a little obstruction on the drain. So let's say that you've got a little piece of cucumber, and it lodges partially over the drain here. And it doesn't completely plug up the drain, because then the analogy gets kind of blows up. But it partially plugs up the drain. So that means that for a given water level, the flow down the drain is less than it used to be before the piece of cucumber got stuck there. So what happens then is after the piece of cucumber lodges there, the water level goes up until it's high enough that it can shove water down the drain in order to balance the water coming in from the faucet again. So it's kind of weird to think about monkeying with energy leaving actually warming up the planet, but you can kind of see it in this sink analogy maybe more clearly. The piece of cucumber doesn't come with a gallon of water. You don't have to dump a whole gallon of water in with the cucumber. It doesn't bring water with it. All it does is it traps, it holds the water in the sink a little longer. And that's what the greenhouse effect does for the heat energy in the planet. It doesn't bring, the pane of glass is not a heat source, but it just impedes the way that water leaves the system. So I want to wind up by bringing back that table that we made of the terrestrial planets, Venus, Earth, and Mars, and see what we have accomplished today with our greenhouse effect. So the solar constant again is higher for Venus than for Earth and Mars. The albedo is very high for Venus, 0.33 for Earth, 0.16 for Mars. The temperature that is actually real for these planets. For Earth, it's something like 280 Kelvin. For Venus, it's lead melting 700 degrees Kelvin. And for Mars, it's like 240 Kelvin. And the temperature of the bare rock model that we did last time was 240 for Venus, 253 for Earth, and for Mars it was 216. But now the temperature for this layer model, if we add one layer to this, for the Earth we come in pretty close. It's now 303 Kelvin. So this model is giving us too strong of a greenhouse effect for Earth. It's warming up the planet more than the real thing. For Venus, the answer we get is 285. So one pane of glass doesn't do it for the greenhouse effect on Venus. The greenhouse effect on Venus, you would need many panes of glass, and the temperature goes up the further down you go into that sort of an atmosphere. So when you do the two-layer thing in lab on next week, you'll see kind of how that works. Most of the carbon on Earth is in calcium carbonate rocks, but because of differences in the carbon cycle between Earth and Venus, most of the carbon on Venus is in the atmosphere. So it's something like 70 bars, 70 atmospheres of pressure of CO2 on Venus. Actually, it would probably feel more like standing at the bottom of an ocean to be on the surface of Venus, very hot ocean, than to be in land with gas, because the CO2 is more like a fluid at that kind of pressure. And then for Mars, we end up with 259. So the greenhouse effect on Mars is not quite as strong as our simple model is either. Anyway, so that's the greenhouse effect, and we will continue on Monday.